everyone. So, earlier this week we have been discussing the valuation of water resources and water services. We did discuss about the different approaches to identify the different components of the value. So, in this concluding session we will be talking about the what is the full value of the water, what is the scale of losses particularly in the urban water supply that undergoes, because that is a loss of value. So, that is what we will be discussing in this concluding session. If you see the component of full value of water, so we have already discussed about the different cost or different value of the water. So, generally when we say that water services or water is under supply either for irrigation purpose or for the domestic purpose. So, the supply cost or the full supply cost typically will include the capital cost and the O&M cost. So, O&M is operation and maintenance cost, which is on a recurring basis, and capital cost is a non-recurring cost which is typically done at the beginning of the typically invested at the beginning of the utility construction or utility installation. So, capital cost or the its depreciation and replacement cost either can be taken. So, that way the combination of these two gives us the full supply cost. Then there is opportunity cost, like what are the alternate uses of the water if that water is not being used for this purpose, for any alternate purpose, how much cost or how much value this water contains. So, that will be estimated under opportunity cost, and then there are economic externalities which are coming from the which are being generated from the other economic aspects. So, this economic externality and opportunity cost again when added, so this gives us the full economic cost. So, your full supply cost plus your economic externalities and opportunity cost in combination will give the full economic cost, and if the environmental externalities is added in that, the environmental externalities in form of what are the impact onto the environment or what is the benefit on the environment. So, this economic externalities and environmental externalities are the two form of externalities which could be either positive or negative, because impact of a utility, impact of a service can be positive also or can be negative also on the environment. Similarly, on the economic aspects of the society, it could be positive or it could be negative. So, whether it is positive or negative, it is taken into the account, and that way the if all things is added, what we get is the full cost of the water. So, these are the different components that are obtained for the full cost of the water. Now, if we need to see application of water or application of a utility or certain particular application or use of water is sustainable or not. So, we need to compute its full cost and the total value also. So, if its cost and value are reasonably in the same range, we can say that use is sustainable, or other way you can say that use is actually not sustainable. So, that way if you see the full cost, we already discussed what are the O&M cost, capital cost, then there is opportunity cost, economic environment and environmental externalities. Similarly, on the value side we get the value of user of water, then what is the net benefit from the return flows, because if water is being used for a purpose, there would be some return flow out of that water. So, what is going to be the net benefit of that, then net benefit from the indirect uses to the society, then adjustment for the social objective if there are any. So, all those gains are will in combination give you the economic value of the water. And if the intrinsic value is added to this economic value, like intrinsic value due to the intrinsic factors of the utility operation. So that in combination gives the full value. So that way full value and the full cost can be estimated and eventually can be compared for the sustainability analysis purpose. So this is an example problem of a similar scale. So where the gross value of agricultural output with irrigation in a state is given as 1,29,000 rupees per hectare, when two water intensive crops paddy and wheat are grown in a year cycle. The gross value of output without irrigation is estimated only 22,000. So this difference will give us the difference due to the irrigation. Okay. Now the average cost of input including fertilizer, labor and irrigation is 87,000 per hectare, and input expenses without irrigation is 19,000 per hectare. So irrigation requirement are also given for paddy and wheat, which is for paddy it is 1640 and for wheat it is 420. So that way if you see the total irrigation requirement in a year cycle is going to be the 2060 mm per hectare, or if you want to convert in a meter cube, so one needs to multiply with the area. So this 2060 mm would be 2.06 meter, and then you multiply with 10,000. So what you get is 20600 meter cube per hectare water is being used for irrigation. Okay. Further you see that the total output is 1,29,000 at a cost of 87,000. So what is the gain with irrigation? So that is going to be 129,000 minus 87,000, which is the cost. So that way this difference, which is going to be the 42,000, will actually be the net profit for the irrigated crop and in a year, while opposed to that you have 22,000 is the value of the crop production and 19,000 is the value of the expenses. So you see the net gain here is 3,000 for non-irrigated. So 22,000 minus 19,000. So net gain here is just 3,000 for non-irrigated. So when you are putting this much of water for irrigation purpose, your income is actually changing from 3,000 to 42,000. So that way we can determine the per unit water how much additional income has been generated, and that is what will give us an idea of the sort of economic value of that water. Irrigation and 3,000 without irrigation. So additional output or additional value due to irrigation is 39,000, and water input is 20,600. So net value of output in terms of rupees per meter cube is 1.89. So that is the net value of output from the irrigation. So if you see the question again, so that is there. Now for the total cost, it further says that the net benefit from non-irrigation uses are estimated as 1. So there are additional benefit from non-irrigation uses of that water, which is 1 rupees per meter cube, and net benefit from return flows, the after irrigation whatever flows is returning to the system of is 25% of net value of output in agriculture. So the net value of output was 1.87. So, it will be taken as 1/4 of 1.87, which is 25% of 1.87. Based on the volume of recharge. Also note that the value for the adjustment for another social objective is estimated as 2.8 rupees per meter cube. So, that way you see that 1.89 was the total value. Okay. We have 1.89 as the net output, then we have other benefit, non-irrigation benefit as 1 rupees per meter cube. These are all per meter cube in rupees, and return flow is 25% of the net value of this. So, basically 25% of 1.89. So, 0.25 times 1.89, which will be 1.89 by 4. So, which is 0.4 and around 0.47. So, 0.47 is going to be coming from here, okay, and then the adjustment for other social objective is 2.8. So, the summary of this is going to be the net gain. Now, for the full economic cost of diverting water to the agriculture, if O&M cost, capital cost and pumping cost are 0.2, 3.8 and 1.5. So, there are 3 types of cost: O&M cost which is 0.2, pumping cost which is 3.8 and capital cost which is 3.8 and pumping cost which is 1.5. So, these are the 3 costs. Assume that the the opportunity cost is also given, that opportunity cost for the urban and household sector of that water is 3 rupees per meter cube. So, this becomes your opportunity cost. Assume that the data corresponding to the intrinsic value and net impacts to the environment are missing. So, externalities are missing. The uppermost component in the tables which we are seeing is actually missing. So, eventually you need to compare the sum of this with sum of this in order to see if the system is sustainable or not. So, that can be seen here. So, that is your total economic value and total economic cost. So, if you see the total economic value as we were discussing earlier, we have estimated. So, 1.89 is from the crop output, then adjustment of social objective is 2.8, non-irrigation usage is 1 and net benefit from return flow is 0.47. This value is unknown to us, and this makes the total economic value is 6.16. On the other hand, the O&M cost is 0.2, capital cost is 3.8 and pumping cost is 1.5. So, this is the total cost and then added opportunity cost, because otherwise the water would have gone to the domestic sector is 3. So, this makes a total of 8.5. So, now you see the, although the like environmental cost or this thing is unavailable. So, if you exclude the unavailable factors, you see that the total cost is actually more than the total gains. So, that way this system may not actually be sustainable for the irrigating these crops in such a fashion. So, this kind of analysis can actually lead to conclusions related to the appropriate or beneficial social uses of the water. Now, when we are assigning a value to the water, so there is a huge water which undergo losses, and that also needs to be encountered. Generally, when we say that okay, we are pumping this much water and then supplying here and there, so either for irrigation purpose or domestic sector. Irrigation sector, it is okay because it is based on the per area hectare and mostly water is not quantified in terms of meter cube or specifically. However, for domestic sector it is very important because domestic water is also incurs larger costs. It needs purification, it needs processing. So, there are expenses of infrastructure, there are expenses of chemical treatments, all disinfection. So, all these expenses makes the water costly, and after these expenses are done, if water is not meeting its intended use, if it is getting somewhere lost in between supply systems, so that sort of creates another problem. So, water losses are that which has been the water which has been produced and is lost before it reaches customer. So, that is what typically is referred as water loss. Now, worldwide water utilities face losses in the range of 5 to greater than 60%. So, at places the water losses are actually higher than 60%. In India also, average water loss ranges between 35 to 40% generally. However, if you see the entire range, it is as low as maybe 7-8% for very well managed utilities like Jamshedpur and such places, to as high as over 60% in many poorly managed city, where in fact there is no proper accounting of how much water is getting lost, because the systems are unmetered. So, people do not know precisely how much water is actually not reaching the intended consumers. The losses can either be real or can be apparent, which sort of means that from what is the form in which they are originating. So, real losses are actually truly physical losses and a form of water in the distribution system, including like if there is a leakage or system overflow, if your storage reservoir is overflowing, tank is overflowing, there is a fracture in the pipelines. So, there is huge water is getting leaked from that pipeline. So, those kind of physical losses, which actually is losses in true sense, is actually taking place. So, these are referred as real losses or physical losses. Okay. These losses inflate the water utilities production cost, because if let us say for example 20% of water which is intended to supply is getting lost somewhere through leakages and other means. So, that means the utility has to bear the burden of additional 20% water, and probably that will be translated to resource. So, it makes the it puts an additional stress onto resource as well. So, utility which is having a loss of for example say 20%, and if they want to supply 100 LPCD water to their consumers, so probably they will have to extract water at a rate of 120 or 125 LPCD, so that even after the losses they can able to supply that 100 liters per capita per day to their consumers. So, for the supplying of 100 LPCD, the stress onto resource is going to be higher. So, those kind of implications are attached to the physical losses. There are apparent losses which are actually non-physical losses, and they occur in the utility operation due to the various reason, which could include the metering inaccuracies. So, if there is inaccurate metering, means it is not getting accounted where that water is going, or if there is a handling in the data error, or if there is a theft, okay, or these sort of like issues actually tend to make water unaccounted. We do not know where that water is going, and it is actually considered as a loss, though in real sense that water is not lost, it has maybe gone for some uses, but not recorded properly. Okay. So, either it is gone through stealing, or somebody has stole that water, or it has basically been supplied but not recorded due to metering inaccuracy or data entry errors or this kind of system. So, this type of losses usually put financial stress onto the utility, because they do not generate any revenue. If you are not having an accounting of these waters, even if they have gone to some sort of uses, but if one is if the utility is not having record of it, in their record book it is actually entered as a loss. So, that is the class of the apparent losses. Now, you see, when the water is supplied, it actually it can go two routes. So, one is the authorized consumption, which is properly metered, which utility knows where water is going, and then among the authorized consumption, again it can actually go to the meters which are billed properly and on which utility generates a revenue. So, this is referred as revenue water. Okay. On the other hand, some part of this is actually is known and is recorded. Utility know that this much of water is going for this purpose, but they do not charge that. At times many institutions are made the water charges for several institutions or public utilities or some, let us say, recreational facilities are made free by the utility itself. So, those water consumptions, although are recorded that okay, this much water has gone for this particular purpose, but that water has not generated any revenue. So, that cannot be included in the revenue water or the water which has generated revenue. Then there are water which is not recorded, okay, which is not authorized consumption. So, the unauthorized consumption, as we were discussing, could be either in the form of leakage, if there is leakage somewhere. So, those kind of losses, which is your real losses, which one can never sort of get the knowledge of. And there are apparent losses which are due to stealing, theft, or inappropriate metering inaccuracy, record entry inaccuracy, system failures. So, these kind of losses. Now, you see, all three of these components, whether this or this or this, or either like even if it is authorized but unbilled consumption, so either that or your real losses or your apparent losses are not generating any revenue. So, this in total is called non-revenue water or NRW typically. So, this NRW in these ages is a term frequently coined by the water utilities to get an idea of how much share of their water is generating revenues and how much share is not generating any revenue. So, the share that does not generate or does not produce any revenue is referred as non-revenue water. The International Water Association, which is IWA, has actually given a proforma for water budgeting of the water utilities. So, that is the in the IWA best practice manual, the IWA suggests, International Water Association suggests that the budgeting of water for a water utility is to be done in a proforma which is sort of prepared after too much of deliberation. So, again they say that it almost state the similar thing which we are discussing earlier. So, there would be authorized consumption which could be billed or which could be unbilled. Now, the billed authorized consumption could be either from metered or unmetered connections. So, even if it is not metered, even if let us say some consumption is not metered, there are bulk consumption which utility is just sending unmetered connection, but they are getting some charge onto that water. So, that should go to the revenue water because it is generating revenue. On to other hand, the unbilled authorized consumption, which is either metered or unmetered in the any form, is actually should be coming to the non-revenue water as it is not generating any revenue. And of course, the water losses, which is either apparent losses, which are also called as commercial losses, the unauthorized consumption or metering inaccuracy. So, they will be non-revenue water, and real physical losses, which is either leakage in the transmission and distribution lines, and then how much is the leakage and overflows at the storage tank, and then leakage on the service connection up to the customer meters. So, combination of all three, although they probably needs to be calculated independently, because if you want to do a water budget in this proforma, you have to compute all these independently. So, how much it is total is there which is adding to the non-revenue water. The independent calculation in a way helps to identify the real problem areas, where is the problem and is at a larger scale, and then one can actually sort of take remedial steps in order to improve the situation. For example, let us say you figure out that there is leakage in transmission and distribution lines is negligible, and leakage in the service connections are again negligible. So, that means your major physical losses is coming from the storage or overflow tanks, and you need to put attention there in order to control it. Okay. So, those kind of implication can be drawn when it is independently estimated all the components of physical losses or commercial losses. The losses, the physical and commercial losses in combination are typically referred as water losses, which is given a term UFW, which means unaccounted for water. So, this unaccounted for water is essentially the combination of apparent losses and real losses, and if one adds the unbilled authorized consumption, which is accounted but not billed, then you get the total non-revenue water. So, that is the difference between the UFW and NRW, where NRW includes authorized unbilled consumption also, while UFW does not include that. So, that way the estimate of losses can be made for water utilities. Now, for the purpose of estimation of the losses, or for the purpose of valuing water or quantifying water, one needs to know how much water is being supplied or how much water is being flowed. So, for larger irrigation project and all that, we have canal, and then we can measure the velocity or the overall discharge in those systems, but in the domestic sector it is done through the water meters. So, the typical water meters means water meters need to be installed at the consumer end probably, in order to know the consumption of a consumer, a specific consumer. So, the water meter of course, as the name suggests, is the process of measuring the water. So, it generally the water meter that comes will give the instantaneous flow reading as well as a cumulative flow reading, that how much water has passed through this meter in a specified time period. So, that way they will measure the volume of water used by the residential or commercial building, which is supplied by a public water utility. Typically they can be used as source as well, okay, or throughout the water supply system for determination of flow at the different juncture or different points. Now, the metering of users for water is a critical aspect, because it incurs huge cost. So, if all the consumers has to be metered, so there will be significant amount of cost, and that to avoid that there are different metering regimes that are proposed, because many countries in the United Kingdom adopt a policy of allowing households to choose if they want to meter or not metered. Many places metering is intensely not provided. Okay. There has been studied which has been sort of concluded that it may be in fact socially or economically efficient to not to meter all the customers, because the advantages coming out of the metering all the customers may not be significant and may not be justifiable. So, in such cases the optimal metering of water can be done. So, there are different regimes for metering water uses. It's there is a ratable value system where there is no metering done, then there is a universal metering where all connections are metered, then there is a optimal and decentralized metering where efficient number, optimum number of meters are calculated and installed, and this optimum number can be computed based on the social efficiency, which gives you the optimal metering, or the utilities efficiency, which generally gives the decentralized metering policy. So, those kind of metering can be adopted. Universal metering may not be encouraged at every time though. Now, the when we get an idea of the value of the water or the price of the water, fair share of the value of the water, one can adopt these several economic instruments for water management. So, these economic instruments typically used market based signals that motivate desired type of decision making, what type of decision is to be made. So, they either provide financial reward or for the desired behavior, or impose certain type of cost, okay, for undesirable behavior. So, for example, we see that, okay, the optimum use of water is this, or value of the water is this, here is, these are the option values of the water for alternate uses, and this might be the more socially relevant options, or in order to, let's say, cut down the value. So, for example, in a domestic tariff system, you can say that, okay, the consumers which are using water less than 10 kiloliters per day will pay small charges, just token amount of charges, because they will be get rewarded by the utility for water conservation, while the consumers which are consuming, let's say, more than 15 kiloliters will pay much higher prices, because as a penalty for the using high water, penalty for consuming more water, or probably going for the wasteful uses of water. So, those kind of economic instruments can be added in the management practices, in the tariff designs and all that, which we are going to discuss next week. So, this is to be basically seen. Now, there are various economic instruments through which it can be managed. There are property rights, then fee based measure, we can put fee, charges, taxes, deposit, refund, all these things. Then there are liability and assurance. So, what kind of, when, let's say, somebody owns a water body, or somebody is given a responsibility, what are their liability rules, and what are various types of bond that can provide strong incentive to avoid environmental impacts and clean up the resource. And then tradable permits, so that these like they can provide a mechanism for minimizing the social and private cost of meeting a cap onto the various type of emission. So, these various water management principle can be adopted based on the economic instruments, mostly through fee, charges or taxes, and it could be let's say, for example, for water services we can have a like tariff which includes for drinking water, sewage, irrigation, raw water, industrial uses, we can put a tariff for that, or in the form of charges, or in the form of basically fee. At times we can put abstraction charge or pollution charge. If somebody is abstracting water or additional water from a resource, he need to pay abstraction charge, or if somebody is releasing or emitting pollutants into the natural resources, into the natural waterways, he need to pay a pollution charge, which basically polluter pay, following a polluter pay principle kind of scenario. So, those kind of strategies can be employed to manage water, and we will, taking clue from this, we will discuss the how the water tariffs are set for the particularly targeting the urban water supplies in the next week. So, we will end this session here for this week, and next week we will be talking about how water is priced and what are the typical criteria or constraint or different pricing structure that are adopted for pricing water. Thank you.